derived from the Blasius solution. So I'll direct your attention to table 7.7 again. And let's start there. And you need to keep your book open to that because I'm going to be referring to it constantly today. The first correlation under table 7.7 is the boundary layer thickness relationship, equation 717. The geometry is flat plate, and the conditions are that it's laminar flow, and the fluid properties are evaluated at film temperature, which is T7. Okay. The next equation is C, F, comma X, which stands for the local coefficient of friction coefficient, and that's equation 718. That's also a flat plate, and it's local, laminar, and again conditions at T7. So that leaves us with the remainder of the table properties to go through today, and we're going to do that. Okay, so let's begin. We're going to start by non-dimensionalizing some variables. All right. We're going to let u, the velocity in the x direction, divided by u infinity, be defined as u star. Similarly, we're going to let T, temperature in the boundary layer, minus Ts, the surface of the plate, over T infinity minus the surface of the plate equal to T star. So we have introduced two non-dimensional variables. One is a non-dimensional velocity variable, u star. The other is a non-dimensional temperature variable, T star. If we then take the differential of T with respect to y, substituting in for T star, we end up with T infinity minus Ts is equal to the partial differential of T, the partial differential of T star with respect to partial differential of T with respect to x is equal to T infinity minus Ts times the partial derivative of T star with respect to x, and then partial of T with respect to y is equal to T infinity minus Ts times the partial of T star with respect to y. And lastly, partial of u with respect to y is equal to u infinity times the partial of u star with respect to y. So we can make those three transformations, and then we will substitute those into the energy equation. Okay, and our result will be as follows. U times the partial of T star with respect to x plus V times the partial of T star with respect to y is equal to alpha times the second order partial of t star with respect to y. And with that, we'll have the following boundary conditions. They are at y equals 0, which means at the surface of the flat plate, t star will be equal to 0 and u star will be equal to 0. At y approaching infinity, or in other words, out to the free stream, t star will equal 1 and u star will equal 1. The significance of that is the boundary conditions for temperature and velocity are the non-dimensionalized temperatures and velocity are identical. So in other words, at the boundary condition, t star and u star are both equal to 1, and at the flat plate, t star and u star are both equal to 0. So the boundary conditions are the same. And since we have u star and t star are identically mathematically defined. In other words, momentum equation and the energy equations are the same when Prandtl number is equal to 1, which means when alpha is equal to nu, we can say that the partial of u star with respect to y, evaluated at y equals 0, is identical to the partial of t star with respect to y, evaluated at y equals 0. Now, what is the significance of this? In brief statement, the significance is that we can use the results of the Blausius solution to solve the temperature. How are we going to do that? And the heat transfer. Okay? Let us recall the energy balance at the wall. Okay, the energy balance at the wall, we said was H is equal to minus K partial of T with respect to Y, evaluated at Y equals 0 over Ts minus T infinity. If you'll recall, we did that when we first started the convection clock. Okay, well, we can then transform this and say that H will be equal to minus K times the partial of T star with respect to Y, evaluated at Y equals 0, times T infinity minus Ts over Ts minus T infinity. Obviously, a couple of nice things happen. These terms cancel out and with it the negative sign. And we are left with H being equal to K times the partial of T star with respect to Y, evaluated at Y equals 0. In other words, at the surface. So, from the Blausius solution, we know that the partial of u with respect to y, evaluated at y equals 0 for the Blausius solution, is equal to u star times u, not u star, u infinity, times the quantity u infinity over nu x to the 1/2 times 0.332. Okay? That's where we ended up last time. All right? And partial of u star with respect to y, evaluated at y equals 0, would be equal to the partial of u over u infinity with respect to y, evaluated at y equals 0, because we define u star as u over u infinity. U infinity is constant, so that comes out. So we're left with 1 over u star times u star, 1 over u infinity times u infinity times u infinity over nu x to the 1/2 times 0.332. So these cancel out, and we're left with simply u infinity over nu x to the 1/2 times 0.332. And since the equations are mathematically identical, we can say that the partial of t star with respect to y, evaluated at y equals 0, is equal to partial of u star with respect to y, evaluated at y equals 0, or it is equal to 0.332 times infinity over nu times x to the 1/2. And now we can substitute. And we obtain the following. We know that h, a function of x down the flat plate, is defined as k times this. So we know that this is equal to, we know that by this, I mean the partial of t star with respect to y evaluated at y equals 0 is equal to partial of u star with respect to y evaluated at y equals 0. So we can make that substitution, and we have the following result. K times, let me write away this book, 0.332 K times u infinity over nu x to the 1/2. Okay, now, typically, you're going to find, I'm not quite sure why we do it, or why it's not in the discipline, but we don't typically list h. What we list is the Nusselt number, which contains h. Okay? So we're now going to transform this into the Nusselt number. So we have this expression for the local heat transfer convection coefficient. This is for laminar flow, flat plate, okay? All the conditions we started with in the Glasgow solution. And this will lead itself to the local Nusselt. Now, get used to seeing things written this way. If we're going to have the local Nusselt number, I want to say that too many times. You will see it written as Nusselt, N-U, with the small s. If we talk about the average Nusselt number over a flat plate, you'll have the Nusselt number with a bar over the top. Instead of x, it will have L, signifying that it's over the entire length of the plate. Okay? Are local coefficients particularly valuable? What do you think? Not really. We're more interested in heat. We'd be more interested in heat transfer over time. Okay? In general. But you get from one to the other. So here's the local Nusselt number. Okay? Go to table 6.2. Open your books to table 6.2 and tell me, what is the Nusselt number equal to? Flip it open. HL over KF. What is that? Is the K of the fluid. All right, that's K of the fluid. So we have H, we have L, and so we need to substitute these, and the Nusselt number then, the localized Nusselt number, turns out to be H, which is a function of x, times x over k, or this turns out to be 0.332 times the Reynolds number, a function of the x, to the 1/2. And this is for Reynolds number equal to 1. Okay? Now, I want you to look at your book, table 7.7. Told you we were walking through this today. The next equation down is the localized Nusselt number for laminar flow over a flat plate. And it's slightly different. Okay? And why is that? Because it has been modified to account for small variations in the Prandtl number. Specifically, for Prandtl numbers, Prandtl numbers greater than or equal to 0.6 and greater than or equal to 0.6 and less than or equal to 50, we will write the localized Nusselt number as being equal to 0.332 times the Reynolds number to the 1/2 times the Prandtl number to the 1/3. And this is the equation you would use if you were asked to solve for the localized heat transfer convection coefficient for laminar flow over a flat plate. Okay? This is equation 721. It is the third equation in table 7.7. So now you know where the three equations came from, and the top three equations in table 7.7. Okay? Now, I want you to direct your attention to the next two equations. In the next two equations, you will see that we have a coefficient of friction with a bar over it, okay? And it is, if you look over, it's still flat plate, but this is our laminar average. So this is the value which is averaged over the entire flat plate. Similarly, down below that, one more is the Nusselt number averaged over the entire flat plate. How do you think we get that? Pardon me? Integrate over the flat plate and divide by that, right? So let's take a quick look at how that's done. And then we're going to move on to other things. So, the average quantities are obtained for the average values of CF and the Nusselt number over the flat plate. We integrate from the leading edge to the end of the plate. Now you could integrate halfway if you wanted to, but that doesn't seem to make a great deal of sense. Okay? I mean, you could, then you'd be 1/2 L. All right, and the values are CF. I'll use L, I like that better than X, and you'll see that also in the book occasionally. 1.328 times the Reynolds number to the minus 1/2. This is equation 724. And the Nusselt number is equal to 0.664 times the Reynolds number to the 1/2 times the Prandtl number to the 1/3. And this is equation 725. Now, I'm going to stop here a moment because you have just seen, at least to the best of my knowledge, all of the analytical solutions to finding H for flat plate flow of this nature, okay, over the last year and a half, or less than half. So you ask yourself the question, there's a lot more stuff in this table. Where does this stuff come from? Well, the stuff comes from years of PhD dissertations, all right? And in comparing DeWitt, one of the values of this textbook is that they have, well, actually, one's dead. I think they both may be dead right now. But while they were alive and working, they did a marvelous job of searching the literature and coming up with the best correlations that they could find from the research to predict values of heat transfer convection coefficient for different geometries and different conditions. And chapter 7 is the what we call the external flow chapter, okay? And we're going to continue to talk about this next time as well, but I want to take a pause now, and I want to put things in perspective for you. All right, we have fed you a pure fire hose for the last 2.5 lessons. Beautiful partial differential equations. You've even had a chance to do some homework on it. You have a chance to raise your grades by doing bonus work on it. These are all good things. And you have now seen the results of these represented in the first 5 equations of table 7.7. And that's it. Everything else is from experiments. Okay? And we're going to use the experimental results to work real problems. But I want you to do, I wanted you to be able to appreciate that there is a mathematical background for this, and that's where these equations came from. So it's not all waving your hands. There's a lot of math and science, or a lot of math that goes into it, but there is that result ending up with these equations you see right here. Everything else is essentially empirical, produced by equations. So now, at that point, before I go on to continue the class, let's take a moment to reflect on where we're at. We have started the convection block. We have done the math, so to speak. We have now gone through chapter 6 with the Reynolds analogy and all the mathematics associated with that presentation, the PowerPoint. And then we got into chapter 7, and we are dealing with flat plate flow. And we are dealing with flow over a flat plate. Okay? This is called external flow. And not tomorrow, but in the next lesson, which will be on Monday, we're going to look at external flow over cylinders and spheres. Okay? That's what we're going to be doing. And then, the next lesson, we're going to move into chapter 8. And chapter 8 is internal flow. Okay? And then, we're going to move into chapter 9. What's chapter 9? Free convection. If you think all the way back when we were starting out the course and doing the thin experiment, we dealt with some equations from chapter 9. So we'll be doing free convection, and then what comes up?
Radiation.
Yeah, but before radiation. Well, let's talk about it here for a second. What do you all love the most, other than bonus homeworks and we're talking about your exam. All right? So if you look at the syllabus, we have today's lesson 22. Monday's lesson is external flow over cylinders and spheres. Then we move in next Wednesday into hydrodynamic and thermal considerations for internal flow, that is flow through pipes and cylinders, things of this nature. Then we have Friday as spring break. Then we come back and we do the energy balance for internal flow. And we do look at another analytical solution, the laminar flow solution for internal flow. And then we look at the empirical relationships for pipe and tube flow. And then we do free convection, empirical formulas for free convection. We have a review class, and then we have our exam number 2, which is on the 11th paper. So it's going to come fast and furious when we get, as we move along. And then we do 3 classes on heat exchangers, which are all applied. And then we do the last 1, 2, 3, 4, 5, 6, 7 classes on radiation. Okay? Pardon me?
We don't get a snow day on Monday.
Even if we get a snow day, it doesn't matter.
I know. We just have it in on Friday.
I look forward to snow days. All right? Because I really like teaching 2 in a row. It'd be great to be able to teach like 5 lessons if you transfer all in one day. Although getting all those homeworks in the next time would be a tough one. All right, and then we have our exam number 3. We're going to have that during the final block, okay? And I don't know what we'll do. We may do it on a Saturday. I don't know. I like doing it on a Saturday because there's nobody else around. What are you shaking your heads for? Honest to goodness. Colleges went to school on Saturday through about 1970. Through the 70s. Routinely, universities had Saturday classes. Routinely. Yeah. When I went to college, I had classes on Saturday. And I wasn't alone. Now, I went to West Point, so it was a little bizarre over there. But a lot of places had Saturday classes. A lot of places had Saturday classes.
You can't get it.
They started lightening things up. People 2-day weekends. I don't know why. No need for it. No need for it at all. All right. Does that help you put things in perspective a little bit? Let me tell you right now, some of you are going to write at the end of the thing when you do your review, we need more time for radiation. I know we need more time for radiation. So if any of you would like to know where we can crowd more stuff into a class, let me know. We'll add it in. But I've done my best to crowd as much into this course as I can possibly crowd. And there is not much room to crowd much more. This is, if you go to graduate school and take heat transfer classes, you will probably take a separate graduate level heat transfer and convection, a separate graduate level class in conduction, and a separate graduate class in radiation. So you can imagine you'll get a great deal more in depth in each one of these three topics. All right. And now it's time to, I'm not going to write on the board, I'm just going to talk to you a little bit, but I want you to open your books. All right? Open your books to table 7.7. Because I'm not going to write all these equations on there, I'm going to talk to you about them. Okay? All right. So, we have talked about equations 720 through 724 and 725. A hint. What is the best way to use this table? Well, first of all, you have to look at the notes at the bottom of the table. All right, if you turn the page over, you will see there are several notes. Okay, use them. All righty. What is TF? That's a good question. TF is the film temperature, and it is the surface temperature and the fluid temperature. So it'd be TS plus T infinity, and I'm trying to remember where it is. It's hidden. That always confuses people. It's the fluid temperature and the surface temperature added together and divided by 2 average. Okay, that's the TF.
On the next page, at the bottom of
What
the-
page?
It's on 456 at the bottom, underneath table 7.9.
456.
Oh, sorry, I have heat and mass transfer, never mind.
You have heat mass transfer?
Yeah. That's that.
Isn't it note C?
That's what it is. So it's in here somewhere. Now I got it highlighted, but I can't find it right now. So anyway, that's what it is. Okay. So let's go down. It is the surface temperature plus the ambient fluid temperature, which is flowing over the surface, added together and divided by 2. Pardon me?
TS plus T infinity over
No, not T infinity over T. T infinity plus TS divided by 2.
2. Yeah.
Okay. Yeah. All right. All right. See how I got my table here? This is very handy. All righty. So what do we have here in the table? Other than a nicely colored table. All right. We go down here, and I want you to look just at the big picture for a moment. All these equations and equations above my pink line here, first pink line, are for flat plate flow. Okay? They're for flat plate flow. So you've got a flat plate with fluid flowing over. Sometimes the fluid will flow over one side, sometimes you'll have to calculate it flowing over both sides. All right? After that flat plate ends, you will see 3 equations for flow over a cylinder. Now, what would we typically be dealing with? A pipe. And this is cross flow. These equations, we're going to talk about this more next time, but these are flows where the pipe is perpendicular to the direction of the longitudinal axis of the pipe is perpendicular to the fluid flow. If you have a pipe where the fluid is flowing over it, depending on the diameter of the pipe, how do you think you might analyze that? As a flat plate. If the curvature is not too great, And there's actually a criterion there we'll talk about later in Monday's lesson about how you can identify if you can essentially unroll a tube and treat it as a flat plate. Okay? And then beneath that is the one lonely empirical equation for a sphere. Okay? And then we have equations for falling drops, tube banks, impinging jets, and packed bed of spheres. Now we're not going to work any problems on those, but you should know that they're here in case you ever need to find an empirical equation for those. They're contained here in comparative weight. I had to use one of these one time when I was studying thermal energy storage. Thermal energy storage systems, we don't talk about them here, but essentially they're ways of storing energy and drawing it in and out. And one of the ways to do that is manufacture of these about 5-inch diameter plastic containers filled with water, which you put into a big box of concrete, and if you blow air through it, it heats them up, and then you can reverse the airflow and extract heat later. Typically used for air solar systems, flat plate solar systems. And you would need the packed bed correlation to best analyze that. All right? So, having said that that's the big picture, what are we going to do for the remaining 10 minutes today? We're going to take a look at the other correlations. All right? So let's jump down to 726. 726 has the Nusselt number being equal to 0.564 times the, I always forget that one because I don't use it very much, the Pecklet number. And the Pecklet number is the Reynolds number times the Prandtl number. I could have just said the Reynolds number times the Prandtl number. They call it the Pecklet number. So that's called the Pecklet number to the 1/2. That's for very low values of the Prandtl number. I can honestly say I've never given a test problem or a homework problem where we've used equation 726. So before you use that, recall that by having said that. All right. The next is for, because that is a Nusselt number for a local laminar flow, and that is similar to what is up in 721, except it's for very, very low Prandtl numbers. The next thing down, we've jumped now to turbulent flow. Most flow is turbulent. Most flow is turbulent. How are you going to test to see if flow is turbulent or not?
Yeah, the Reynolds.
Well, we covered this actually at the beginning of class. The Reynolds number for flat plate is what for turbulent flow? Ten times 5 to the 5th. All right. 10 times, excuse me, 5 times 10. 5 times 10 to the 5th. All right. And what is 5 times 10 to the 5th? 500,000. All right? So, now listen carefully. Sometimes we will have flow which is tripped if the Reynolds number is a function of how far down the flat plate you are. So typically, if flow starts on a flat plate, and remember the drawing I had over here? It starts on a flat plate, and then it jumps from laminar to turbulent. And frankly, and simply stated, the faster the flow, as well as the fluid properties concerned, the faster the flow, the sooner it will transition to turbulent. So, what do we have to deal with that? We're going to have different conditions. If you look down, the Nusselt number in equation 720, all right, let's get back for a second. 728 shows you the coefficient of friction for turbulent flow, local value. 729 shows you the thickness of the boundary layer for turbulent flow. Now that is a local value because you don't get an average thickness of the boundary layer. You're interested in the thickness of the boundary layer at a point, okay? So there's no average thickness of the boundary layer. Make sense? And then you have the Nusselt number, 730, which is for the local value. And then you start having two very interesting equations at the end. And this is a coefficient of friction for the mixed average. Okay? Mixed average, which means we start off lambda and we go turbulent. And that's coefficient of friction. Notice that it's got the L over it, and, excuse me, the bar over it and the L. And then you have the Nusselt number. You'll see that the average value as well. All right. You see that the criteria stated in there is 5 times 10 to the 5th. Okay? All right, now, let me take you back here for 1 second. Open your textbooks now to, and listen, there's really no substitute actually reading the textbooks. On page 423 of the 6th edition, you will see that the two equations, no, that's 24 and 25. For laminar flow, on page 425, you will see the equations for, that I just pointed out, 731 and 733. Now, look down at the bottom of page 425. Underneath equation 733, you should have this highlighted and underlined. For a completely turbulent boundary layer, that is, the Reynolds critical number is equal to 0. A is equal to 0. And that applies to 731 and it applies to 733. Now you say, when would that happen? When does that happen?
Often?
Often. What?
Oh, never mind.
When does it happen? Yes, you do. I'm asking you, so what do you think? Flight. All right, you ever look out of the airplane wing? You sit there and you're looking at the airplane wing. Of course, you're thinking, what will be like if we crash? And, you know, things of this nature. And is that piece of metal really supposed to be bent like that? And why is that mentioned? But look at the front and look at the wing. What does it look like on the wing? What does it look like? Come on, it looks like sandpaper. Why is it sandpaper? We are tripping the boundary layer. That's what it's called. Tripping the boundary layer. A turbulent boundary layer has more energy and is more likely. Is there someone out there to arrest someone? Usually that's what when public safety comes over, you know, to bring in somebody. It's happened twice since I've been here. It's not been me, by the way, but usually they come to me as me and say, well, we're here to arrest somebody. Oh, well, that's just dandy.
One of the CMs.
I don't recall actually who it was. Anyway, boy, I've got off the subject. But turbulent boundary layer has more energy, and it adheres to the surface. And if you're flying in a plane, you want the boundary layer to adhere to the surface. If the boundary layer begins to separate from the surface, as what happens when you begin to climb too quickly, that boundary layer will pull away, and when that happens, you lose your lift, and we've already been there. You lose lift, you stall, you begin to fall like a rock. So to help prevent that, airplane wings will have a rough surface at the beginning to agitate the air and trip the boundary layer, bringing it into a turbulent flow almost from the beginning of the leading edge. Okay?
Is that just airliners, or is that like almost every plane?
Certainly most airliners, which fly with jets. I don't think they do that so much on like Cessnas.
What about like military planes?
Why wouldn't?
Military planes, I don't know if they do or not.
The paint itself is kind of abrasive.
Yeah.
Just for like the
Well,
radar
that's what's on the, most,
ability.
yeah, it is, yeah. Well, you got so much going on military planes because some of them
Yeah.
have radar absorbing paint, so they're semi-invisible, things like that. Okay, so that's when you would have that case. So now, that means you need to remember this page is here, so if the problem says the boundary layer has been tripped at the leading edge, all right, you can work, you go back to these two equations, A goes away, and now you have, if you take away the A, you have equations for fully turbulent boundary layer, fully turbulent flow. All right, one other thing. If you compare 731, before we leave, to equation 731 in the table, lo and behold, just to screw with your minds, there's no A. What's A? 871. Ooh, what's happening? All right, well, what happens is, if you calculate the value of A for a Reynolds number of 5 times 10 to the 5th, guess what number you come up with? 871. Okay? So if you're told that the Reynolds number the critical Reynolds number is different than 5 times 10 to the 5th, you can go to this page, calculate the new A value, put it in, and solve the problem. Is that clear to you all?
Can you say that again?
Okay. On page 425, equation 731 shows you mixed value Nusselt number average for flow over a flat plate. The value of A, shown on page 425, is calculated below in equation 732. And it is based on the Reynolds number, critical Reynolds number. If you use the average critical Reynolds number of 5 times 10 to the 5th, which is the normal, you get a value of 871, and that 871 replaces A, and that's what's shown in table 7.7. But if you are told that the Reynolds number, the critical Reynolds number is different, then you would calculate A and put that A value into equation 731 and use that version of the Reynolds, of the Nusselt. Is that clear? Okay, these problems that I gave you are very straightforward. They're both exam problems from the past, so see how you do on them. They're pretty easy to do.